about conservative versus non-conservative forces and what that means with respect to energy.
So conservative forces, these don't depend on path. So can you think of a force that we know that doesn't depend on path? Like if we're calculating work, right? And I take this golf ball and I move it over here, and then I move it up here. Is that going to give me a different work than if I just do this? No, because remember, it only depends on the initial and final height. Even actually, if I go like this, but I end up at the same height, it doesn't matter. All we care about is the initial and final. So gravity in this case would be a conservative force. Turns out springs also a conservative force because it doesn't matter how much you stretch or compress it, as long as you don't break the spring. All that matters is the initial and final point. So for conservative forces, that means that the work done is equal to sort of the negative change in the potential energy. And that should make some sense, because remember, when we're talking about putting work into a system, when I pick up this golf ball, I'm doing work against gravity. And that means the change in potential energy from gravity should be negative, right? I'm doing the work, I'm working against gravity, it has a negative work. And that gives us something that looks like this, okay? So this looks like a lot of math, but conceptually what you're saying is you're doing work against a conservative force, so that gives you a potential energy, all right? And just because we know this plus this equals 0, you can this is just a different restatement of conservation of energy. And so the total mechanical energy is still conserved. So the reason gravity and springs are the two mechanical potential energies we use is because they're conservative, okay? You have to have a conservative force to get a potential energy, okay? And so for some things, path does matter, okay? For instance, is friction a conservative force? No, right? Because friction is a constant. So if I'm using a spring, but I drag something across a table that has friction, right? If that block had friction, as it's sliding, it's losing kinetic energy, even though it's not hitting the spring. So friction is a non-conservative force, okay? So yeah, if it turns out for anything where you're not just dealing with gravity, conservative forces are path independent, and non-conservative force does depend on path. And you'll notice, like, I mean, if you're doing like weightlifting, like this guy over here, are you just working against gravity? No, you have all these other mechanical parts of your body that you have to get lined up to be efficient, right? So you're expending chemical energy, there's other work that's happening, but what is the easiest way to lift a bar? What is the most efficient way to lift a bar? What would the path look like? Straight up and down, right? So you want to move your body out of the way so you get the shortest path. That's not because gravity is a non-conservative force. It's because all of the other forces and torques that it takes to do weightlifting are not conservative, right? There's friction in your joints. There's all of these other aspects that you have to worry about, okay? But just the bar, if you're just talking about the bar, it doesn't matter what path it takes, it'll still have the same potential energy at the end, okay? Which is why if you're efficient, the minimum amount of energy you can expend is just fighting the gravitational potential energy. Everything else is extra energy, and that's not what you want to do if you want to win, okay? So conservative forces, you can get, this is a slightly misleading equation because you guys, I assume a lot of you haven't taken Calc 3. It's really, I mean, this is a derivative. So if you, this is F sub x, it's the derivative of potential energy with respect to x. The way you would write it to be completely accurate is as a gradient. Do you guys know what does anybody know what a gradient is? It looks like this. So this is a vector. And so this would look like this with a negative, okay? If you use the gradient, what it's really saying is it's a partial derivative with respect to x in the x direction, plus a partial derivative with respect to y in the y direction. It's a partial derivative with respect to z in the z direction of the potential energy. Okay. I know that's it's more complicated than we need, but I'd like you guys to see it. So when you see gradients, you'll know they're actually useful for something. Remember, energy is simpler. The math is usually simpler because it's not a vector. But if you're getting a force is a vector. So how do you get that information back? Well, you have to take a three-dimensional derivative, okay? Because forces can be in a three-dimensional space. So they have X, Y, and Z. So when you use potential energy, it's just one scalar quantity. So this gives you back three different types of information from that one scalar quantity. Okay, so cool. Very graceful. Okay, so just as a recap, if you look at the conservative force here, thank you. If you take the derivative of this, you get this. Okay, so if you take the derivative of your potential energy with respect to y, you get the force, which is mg. If you take the derivative of your spring potential energy with respect to x, you get negative kx. Okay, so for our purposes, we only are doing this in one dimension, but I just want you to understand that this is actually the full definition of what we're saying. Okay, so for our purposes, this is going to be fine, right? You just replace s, it's a dummy variable, with x, y, or z, depending on what your force looks like. But in real life, this is the way that we do things. And this will come up next semester, so it's worth seeing now. It's just, you won't have to use it this time. Oh, good, I animated this. Great news. Okay, so let's try this. Okay, let's discuss this one and vote again. There isn't even an E. Okay. Some classes will always have, like, there's a lot of answers, like, of these that don't have E's, and every year I have someone that always answers E, like they just think it's hilarious and they do it every time. And this is a smaller pool, so I haven't had that happening as much. But like, if you have a whole class, if there's 32 people, one of the people is going to answer the thing that doesn't exist. So this one's complicated, and it goes back to this, right? If you take, if this is a function of x, y, and z, right, and you take the derivative with respect to x, that only gives you the negative component in the x direction, right? It's negative because of this negative sign, okay? It's then there's an x, y, and a z component if you're only taking the derivative with respect to x, because that's all that's available on a u versus x graph, okay? Then you're only getting, to be very specific, the negative of the x component of the force on the object, okay? Because it could potentially have y and z, and that's not represented by the graph. And it's negative because there's a negative between the gradient of the potential energy and the force, okay? So the slight subtlety that you don't totally need to understand yet, but this is sort of, when you get to Calc 3 and you talk about gradients, think about what that physically means, okay? They are not going to tell you that, but like, it'll start coming up in physics, particularly in the next semester. We'll talk about gradients with respect to electric potential, like voltage. Voltage is a gradient of the electric field. Electric field is a gradient of the voltage, because voltage is like just a number, and then you turn it back into a vector that has to do with force, okay? We'll get there. All right.